Hello and welcome. Today, we're going to tackle how simple resistors behave in alternating current circuits. Now, I know AC can sound a little intimidating, but I promise you, when it comes to resistors, it's way more straightforward than you might think.
Okay, so let's start with the symbols we use. Over on the left, you've got your classic DC source, like a battery. But on the right, that's the one we're interested in today. That little wavy line tells you it's an AC source. And that simple visual difference, it signals a really fundamental shift in how the electricity is actually behaving.
So here's our game plan. We'll start by comparing DC and AC. Then, we'll get into something called the in-phase relationship. After that, we'll touch on impedance, figure out how to calculate power, and then we'll bring it all home, literally, by looking at examples around you.
Visit youtube.com/avidsystem and don't forget to subscribe.
All right, first up, from DC to AC. Let's just make sure we've got a crystal clear picture of what makes alternating current so different from the direct current we might be more used to. Think of it like this. DC is like a steady river, always flowing in one direction. It's just a constant one-way push. But AC is more like the ocean tide. The current is constantly pushing forward and then pulling back, over and over, while the voltage flips from positive to negative. This is the kind of power that's coming out of the outlets in your wall.
Now, this back and forth motion isn't chaotic at all. Actually, it's incredibly predictable. As this quote says, it follows the perfectly smooth mathematical shape of a sine wave. And it's this predictability that makes AC so incredibly useful.
And here it is. This is our first, and maybe our most important, simple truth for today. Even with all this talk of waves and changing direction, for a plain old resistor, the fundamental rule you already know, good old Ohm's law, it still works perfectly.
So that brings us to our next section, the in-phase relationship. Okay, so if the voltage is rising and falling in this nice, smooth sine wave, what in the world is the current doing?
This is the big question, right? Does the current get left behind? Does it jump out ahead of the voltage? Or is it something else?
And the answer is just beautifully simple. Across a resistor, voltage and current are perfect dance partners. They are totally in sync. When voltage hits its peak, bam, so does the current. When voltage crosses that zero line, the current is right there with it. They are in perfect lockstep every step of the way.
And in electronics, we have a special name for this perfect partnership. We say that they are in phase. It just means that the difference in their timing, their phase angle, is zero. They are perfectly, and I mean perfectly, aligned.
All right, let's move on. We're going to see how this new world of AC introduces some new words. But don't worry, when it comes to a resistor, it's a lot simpler than it sounds.
So in AC circuits, we talk about something called impedance, and we give it the symbol Z. All it is the total opposition to the flow of alternating current. Now, this concept gets super important later when we add other things to the circuit. But for now, let's just focus on our resistor. And here's the crucial point. For a pure resistor, its impedance is exactly the same as its resistance. It's really just a new name for the very same thing. A 100 ohm resistor is still just a 100 ohm resistor. It doesn't care if the current is DC or AC. Its value stays the same.
So, what about power? If the voltage and current both dip into the negative, does that mean the resistor somehow starts generating power? Well, let's see how their in-phase relationship gives us a really simple answer. Okay, so for half of every single cycle, both the voltage and the current are negative, right? They're in phase, so they're both below that zero line at the same time. But what happens when you multiply a negative number by another negative number? Well, just like in basic math class, you always get a positive.
And what that means is the resistor is always using power. It never gives it back. It's constantly taking that electrical energy and turning it into heat, which is exactly why your toaster gets hot. The power waveform isn't a sine wave at all. It's just this series of positive pulses showing that power is always being delivered.
And you're going to love this. The power formula looks almost exactly the same. It's power equals voltage times current, just like in DC. We just use the RMS values. RMS just stands for root mean square, and it's basically just a way to talk about the effective value of an AC voltage. It's the standard way we do it.
Okay, last section. Why does any of this actually matter? Well, because this isn't just theory on a whiteboard. This is at work in your home every single day. Your toaster, that electric kettle, a space heater, an old-school electric iron, seriously, any simple appliance that's just designed to get hot is a perfect, real-world example of what we've been talking about. It's basically just a big resistor plugged into the AC outlet in your wall.
Let's just prove it with a quick calculation. Say you've got a 1,000-watt space heater, and it runs on a 250-volt supply. How do you find its resistance? Easy. We just take that power formula we know and rearrange it a bit. Resistance equals voltage squared divided by power. So that's 250 times 250 divided by 1,000, and that gives you 62.5 ohms. Simple as that.
So, let's wrap this all up with the one big idea I want you to take away today. When you are dealing with a pure resistor, the world of AC is just as simple and just as predictable as the world of DC. The rules you already know still apply, and everything stays in that perfect in-phase partnership.
You know, we've seen that resistors are easygoing. They just go with the flow. But that leaves us with a really fascinating question to think about. What happens when you introduce a component that doesn't like to change? A component that actually fights back against that oscillating current? Well, that's where things start to get really interesting. Thanks for joining me.
Thanks for watching.